today I'll be presenting our work Pandawan, quantifying progress in Linux-based firmware rehosting. The Internet of Things has grown so much nowadays that we find billions of these devices connected to the Internet. Unfortunately, as most of you probably know, IoT is very famous for its security issues. For example, in December 2022, we observed almost 11 million attacks involving these devices. And the most worrisome thing is that these attacks not only increase in number, but become more complicated as time goes by. So that is why, as researchers, we have to make sure to safeguard these devices about threats that will come in the future. Fortunately, there are a lot of prior research work that analyzes the firmware that runs in these devices, and specifically through rehosting techniques. When it comes to Linux-based firmware, there are works that analyze either its user-level aspect or its kernel-level aspect. However, current solutions lack two important features. First, they do not rehost and analyze both the user and kernel-level aspect of the firmware holistically as a unit. And second, there are currently no techniques that enable the objective comparison of different rehosting approaches based on their emulation capabilities. So why do we need these features? We need the holistic analysis so that our rehosting methods get closer to how firmware works in real-world physical IoT devices. And we need the comparison of rehosting systems so that we can measure the differences between the rehosting frameworks and also their progress in rehosting. So let's talk a little bit more about these two missing features, starting from the holistic rehosting and analysis. While in theory, FirmSolo, which is our prior paper published in USENIX 2023, can be considered as the only rehosting system that supports both user and kernel module code firmware rehosting. In practice, FirmSolo mainly focuses on rehosting the kernel modules within IoT firmware. In order to do that, it configures and builds custom kernels that provide important functionality required by the IoT kernel modules in order to load into these kernels and then be analyzed. Because of this, though, these custom kernels might lack other necessary functionality that is required by the user-level code in order to function properly. And in turn, the user-level code might either crash or exhibit weird behavior, like getting stuck within an infinite loop. So that is why we can say that FirmSolo is not actually capable of holistic rehosting. So let's look at an actual example to understand what I'm saying. So here's the serial log of a firmware that is emulated within FirmSolo. And at some point during the execution of the firmware, it starts printing error messages which actually continue on indefinitely. So what exactly happens? Well, the firmware at some point will enter an infinite while loop, which will exit only if the flush_rootfs function returns a non-zero value. Now, the flush_rootfs function accesses an MTD block character device, and if the access is invalid, then the firmware will print an error message and will return a zero value, which will make the execution remain within the infinite while loop. So why does that happen? Well, because the IoT kernel modules within that target firmware do not make use of any of the MTD block character device functionality. And since FirmSolo configures its custom kernels based on what the IoT kernel modules need, it will not include the MTD char option within its custom kernel, and that's why user space breaks in this case. Now, regarding the second missing feature, which is the ability to compare rehosting frameworks, prior work relies on wall clock time and ad hoc metrics, like, for example, the number of bugs found, to compare themselves with their predecessors. However, each rehosting framework uses a different system design, and that is why wall clock time, along with these generic metrics, are not enough to capture the differences of the systems within the comparison. So let's look at an example of why the wall clock time specifically is not adequate to use for comparing rehosting systems. Here's the timestamp execution of tasks within FirmSolo and FirmAE. you can think of a task as a program name along with its arguments. Now, for the first task, you can see that the execution times are very similar. Same thing with, for the second task, but here we see a small difference. However, as time goes by, the results are way more skewed for FirmSolo execution times, because FirmSolo actually incorporates the rehosting and execution of IoT kernel modules during the emulation of the firmware, and that is why it's much slower than FirmAE. So we can definitely say that wall clock time is not adequate to use in the comparison of different rehosting systems. So for this reason, we introduced the firmware initialization completion detection technique, or FICD, which relies on a simple premise that firmware executes tasks during boot up. And after the initialization phase of the firmware is done, then the firmware should execute either none or very few new tasks without human intervention. So how does this work? Let's actually look at a simple example to understand this. So we define a time frame which you can think of as a timer, and that timer refreshes every time we execute a new task. New tasks are denoted with colored boxes in this case. However, that doesn't happen when we execute a non-new task. In this case, the gray box here is similar or the same as either the green or the orange box. And if the firmware does not execute any new tasks by the end of the timer run, then the FICD technique will mark that point during the emulation as the initialization completion point, which we call IFIN, and then we'll terminate the emulation. Now, that initialization completion point can be considered as conceptually the same for all rehosting frameworks, because each one of them has to undergo the initialization phase of the target firmware that they are analyzing. So what can we do with it? Well, we can use the IFIN point along with metrics that are more relevant to the emulation, like user and kernel firmware code coverage, to basically compare different rehosting systems between themselves. So on that note, I present Pandawan, which is a framework that can holistically rehost and analyze Linux-based IoT firmware. And Pandawan also implements the FICD technique to enable the comparison of different full system rehosting approaches. Now, as you can see here, Pandawan consists of two components: the kernel augmentation component, which essentially configures and builds a custom kernel for a target firmware, and then the which uses in the firmware rehosting and analysis component to holistically rehost and analyze the target firmware. Also here, Pandawan relies on FICD to compare different rehosting approaches with each other. So starting with the kernel augmentation, Pandawan simply uses FirmSolo to analyze the target firmware and produce a custom kernel for it. Additionally, here, Pandawan uses the Oracle mechanism to enhance that custom kernel with important functionality that is required by the user level code to function properly. Like, for example, the functionality in the example I mentioned previously. The outcome of this process is the custom Pandawan kernel, as we call it, which can rehost both user-level firmware and the kernel-level firmware code. Now, the Oracle is very simple. It actually includes popular configuration options that are commonly used in IoT firmware within Pandawan's kernels. However, Oracle also makes certain that any of these newly added options do not affect the layout of any data structures that are used by the IoT kernel modules within our target firmware to avoid potential kernel module crashes during the emulation. For example, here, the config IP mroute option affects the layout of data structure net, which is used by the IoT kernel module X tables. Oracle finds that, and it filters out that option from Pandawan's kernels. Now, once the Pandawan kernel is available, then Pandawan proceeds to rehost that kernel along with a modified version of the target firmware's file system using the PyPanda dynamic analysis system. To use PyPanda, Pandawan relies on a PyPanda script that also incorporates the FirmAE's networking configuration logic to provide networking connectivity to the target firmware. Now, through this script, Pandawan can also use Panda's built-in plugins like Coverage and Syscall's Logger, and also custom plugins like FICD, which is the implementation of the FICD technique, and the Syscall to K-mode tracer plugin, which I'm going to mention what it does in a little bit, to holistically rehost and analyze our target firmware. Now, Pandawan's analysis is actually twofold. First, it can use FICD to compare different rehosting systems along emulation-based metrics like the number of user-level programs executed and kernel modules loaded, and also the user and kernel module code coverage achieved by each system. Also, the analyst can include other metrics if they want to. And second, it can holistically analyze the target firmware. Specifically, what it does is that it uses a syscall to K-mode tracer plugin to trace system calls that access IoT kernel modules that were loaded by the firmware during its boot up sequence. Then it uses a technique similar to the Moonshine paper to convert these traces for seeds for TriforceAFL, and then we use the TriforceAFL kernel fuzzer to fuzz the IoT kernel modules within the target firmware. Now, we evaluated Pandawan on around 1,500 firmware images, the majority of which originates from the FirmSolo dataset. And we also used 50 more modern images that use newer kernel versions from the Greenhouse dataset. During our rehosting comparison experiments, we used FICD to compare the Firmadyne, FirmAE, FirmSolo, and Pandawan rehosting frameworks. And during our analysis, in general, Pandawan was able to outperform these systems in the average numbers of user-level programs executed and kernel modules loaded, and also in the average number of user-level code basic blocks and kernel module code basic blocks executed as well. For more information about our extensive analysis for these experiments, you can also refer to our paper. Now, regarding the holistic analysis experiments, Pandawan was able to create seeds for 500 firmware images, which we used to analyze the IoT kernel modules within these images. TriforceAFL was actually able to trigger 16 bugs, 6 of which were previously unknown, in 12 kernel modules, 8 of which are proprietary. Of course, we reported all our findings to the respective vendors. So in summary, I talked about Pandawan, which is a framework that enables the holistic rehosting and analysis of Linux-based IoT firmware. And also we introduced the FICD technique, which enables the comparison of different rehosting frameworks based on their emulation progress. Our source code is available publicly, and I'm happy to take any questions. Thank you.